Okay, we have been talking about a derivative, and now we'll extend it to a function, calling it a function. So let me write down the definition. And x is any point that this is defined on. So before we used a, we used a specific point, so that was the derivative at a point. Now x is going to vary, and let us find the derivative at any point. So this is also the slope of the tangent line at any point x. So, for instance, if we look at this, suppose this is our function, and let me suppose these are a few points. The derivative is going to tell us a lot about the function. And before I continue, let's look at what slopes mean or are. If a line increases, then it has a positive slope. If a line decreases, it has a negative slope. They get steeper, so this slope is 0, and this slope is 1. As they get steeper, the slope increases, and this slope maybe is 3. So it increases to infinity or no slope when it's vertical. Okay, that's talking about positively. So when I go over here and I draw the slope of the tangent line at a point, so let me make a little chart. At x equal 1, let's say the slope is about 1. At x equal 2, it flattens out, so let's say the slope is 0. Again, this is just a guess. At 3, the slope of the tangent line, remember the tangent line just touches it at one point, it's decreasing, so it's negative. So at x equals 3, let's say the slope is negative 2, because it's kind of steep there. 4, it's flat, so it's 0. And at 5, it's kind of steep, so let's say it's 3, it's positive 2. So at x, it's 5, the slope is, say, 3, because it's kind of steep. So this kind of represents a function. For 1x, there's one tangent line, so there's slope of the tangent line. This is a function. The derivative represents a function. So this right here represents a function because for 1x, there's one slope. So that's why we say f prime of x is a function, or can be represented as a function. So if let me go back and look at this picture again. When the graph is increasing, so here the graph is increasing, all these slopes are positive. So let me do a little number line up here. From the point where the function starts to here, f prime, the derivative, is positive because the slope is positive. Then the slopes become negative until you get here. At this point, f prime is negative. All the slopes of the tangent lines are negative. And this is a real important idea. As you come over here and take all the tangent line slopes, so between here and here, the slopes are positive again. And where they change, the slope is negative. So f prime is negative, actually. Let's do it that way. So from this right from this right here, we can graph that, say 1, 1, and 2, 0, and 3, -2, and 4, 0, and 5, 3, and surprisingly, or maybe not surprisingly, it's a parabola. So this is the graph of f prime of x, which is a function, so we know it's connected. So this graph right here of f, this graph is f of x, we can get the graph of f prime of x, and notice where f prime is negative is between 2 and 4, and here f prime was positive, it's above the x-axis, and here, again, f prime is positive from 4 to 5. And that's what we said up here. When the graph was increasing, our f prime was positive. When the graph was decreasing, our derivative was negative. And when the graph was increasing, our slopes or derivative were positive. So you always have to keep in mind that the derivative represents the slope of a tangent line. Okay, so let's take a specific function. That right there was really, really important that you understand that. Let's take x squared minus 5x. The derivative is the limit h goes to 0, f of x plus h minus f of x all over h. So the first step in this, let's say first, we're going to do f of x plus h. And this says replace x in the function by x plus h in parentheses. So wherever there's an x, we're going to substitute x plus h. So it's going to be x plus h squared minus 5 times x plus h. Because a function's a rule, and the rule here says square it, subtract 5 times it. So it's it squared minus 5 times it. And it, in this case, is x plus h. So we're going to square it and subtract 5 times it. And we're going to FOIL this out and simplify it. Okay, the second step is right here. We find out what f of x is. Well, f of x is our original function, so that's x squared minus 5x. That's the original. Step 3 is right here. We're going to subtract. So when we subtract, the like terms are going to drop out. They add out. And what's left is 2xh plus h squared minus 5h. The next step is factor out h. Okay, so up here, it doesn't have that in the formula, but we're going to factor out a h, and then step 5, we're going to divide by h, and step 6, we're going to take the limit. So this is just what we do broken down by steps. So 5 was divide by h. So if we divide this by h, we get 2x plus h minus 5, and then we take the limit, we let h goes to 0. That's the distance closing in to our point, and if h goes to 0, this comes out to be 2x minus 5. And remember, that's called the derivative, and that is the slope of the tangent line at any point. So for any x, 2x minus 5 equals the slope of tangent line at x. So let's say if x is 0, then f prime of 0 is negative 5, and that's our slope. If x is 1, then our slope is negative 1, and if x is 2, no, if x is 1, then it's negative 3. Let's take a 3, let's get it positive. If x is 3, then our slope is 1. So, I mean, let's just look at that. At x is 0, our slope of our tangent line is negative 5. So for our original problem, the point that it goes through is 0, 0. Let me go back here. Let me find that where I was. Okay, right here. For the original function, x and y, 0, 0. So at 0, 0, my slope is negative 5. Well, that's pretty steep. So we'll say that the slope, and it's negative 5, so it goes like that. At 1, our original function, if you plug that in, the original function, which was 2x squared minus 5. I forgot a 2 here. Let me go back. I need to fix all this. No, I just did x squared minus 5. Okay. X squared minus 5x. So if I put a 1 in there, it's 1 minus 5 is negative 4. So at 1, negative 4, at that point, the slope is negative 3, so it's a little bit less. And at 3, and the original function is negative 6. So that's about right there, negative 6. The slope is 1, so it's positive here. So if you knew all those slopes, those tangent lines, then you could tell what the function does. And the function probably is a parabola. These are function values. These are function values. These are f prime values. So that's the whole point. If you know the derivative, then you know what the function looks like. Okay, let's look at an important idea now that we kind of know what a derivative is. So an important idea is where does f prime not exist? Where do we not have derivatives? So let's look at example 1. Example 1 is going to have a sharp point in it. So that's something like the absolute value x. That looks like a V-shaped problem. Why not? Well, if you're coming in from this side, the slope of this line is 1. If you're coming in from this side, the slope is negative 1. So right here, what's the slope? You can't have two different limits. Remember, the derivative has a limit in it. The limits of the difference coefficient must be the same. So the slopes must be the same on each side. And it's on a sharp point, it's not. So the first case where it doesn't exist is a sharp point. Okay, what about vertical tangent lines? Right here, at 0, we have a vertical tangent line. Well, the slope of a vertical line is undefined. So the derivative has to be undefined. At that point. So we can't have vertical tangent, well, if we have vertical tangent lines, that means the derivative is undefined. And the third time is if it's not continuous. Because, again, you're coming in from this side, and the slope here looks like that. The slope here looks like that. Again, the limits are not the same. The limits are the slopes. So you don't have the same derivative. So if it's not continuous, there's not going to be a derivative. And finally, something else that's really important in this section is this theorem, and I'm going to prove it, and you need to know the proof of it. If f of x is differentiable at a, then f is continuous at a. So let's do something we know. We know f prime of a is the limit as x approaches a, f of x minus f of a over x minus a. So we have to show, in order to be continuous, that the limit as x approaches a, f of x is f of a. Okay, well that's really easy. What we're going to do is start with this, and we're going to use a little trick. We're going to divide by x minus a, and we're going to multiply by x minus a. Then we're going to take the limit, and that can be broken down. Because they're both polynomial, and we know this exists because f is differentiable, so that's equal to f prime at a times the limit as x minus a. X approaches a, but that's 0, so this whole thing is 0. So that tells us that the limit as x approaches a, f of x minus f of a is the limit as x approaches a, f of x minus the limit x approaches a, f of a. But this is a constant, so that's just f of a. And that's 0, so that says that the limit of x, f of x, x approaches a equals f of a. So f is continuous. That's the definition of continuous right here. So you need to make sure you understand these theorems and these definitions.